It's late. You are staring at your IDE, probably waiting for like a massive build to finish, and you realize something just fundamentally broken about modern tech.
Oh, there are a few things broken. But yeah, I know where you're going with this.
Right. Like the generative AI you're trying to integrate into your app requires a literal warehouse-sized server farm to train.
Yeah, hundreds of GPUs running for months.
Exactly. But somehow developers are cramming that exact same intelligence into the smartphone that's sitting right next to your keyboard.
It is wild when you actually stop and think about it.
It's basically magic. So welcome to the deep dive. Tonight we have a stack of notes from a module titled Quantization Running AI on Your Phone.
A very fitting title.
Yeah, and our mission today is to figure out the underlying mechanisms of this engineering magic trick. We really want to know how you can take a neural network that demands hundreds of gigabytes of VRAM.
Just massive memory requirements.
Right, and violently compress its underlying data structures, but still end up with a model that can, write functioning Python code locally right on your laptop. Okay, let's unpack this.
So to understand the solution here, we really have to isolate the bottleneck first.
Okay.
And the constraint isn't just storage space on your hard drive. It's memory bandwidth.
Memory bandwidth, got it.
Yeah. When an AI model generates text, the processor has to constantly shuttle weights from the VRAM over to the compute units. And, as developers, we're all used to just throwing FP32 at our problems.
Right, 32-bit floating point numbers, because normally memory is incredibly cheap.
Exactly. And FP32 has one sign bit, 8 exponent bits for dynamic range, and 23 mantissa bits.
That's a lot of extreme fractional precision.
It is. But when a model has 70 billion parameters, moving those 32-bit floats across the bus completely chokes the hardware. It just can't keep up.
It's like trying to drain a swimming pool through a garden hose.
That is exactly it. And that is the barrier that quantization is designed to break. It's the process of just stripping away that decimal level precision.
So we're mapping those sprawling floating point values down to much smaller integer format.
Right, down to like int 8 or even int 4.
Which gives us an 8x reduction in size if we drop all the way to a 4-bit integer.
A massive reduction, yeah.
But see, this is where my software engineer brain immediately throws an exception.
Oh, why is that?
Well, if you think about this like asset compression in game development, right? Imagine taking a beautifully rendered, uncompressed 32-bit high-resolution texture map.
Okay, so here you go.
It is pristine, but if you crush that texture's color palette down to just 4 bits, you only have 16 total colors to work with.
Yeah, it would look terrible.
You ruin the asset, you get horrendous gradient banding, blocky artifacts, and the whole thing just looks like garbage.
Right.
But our notes explicitly say that shrinking these AI models from 32 bits to 4 bits results in a surprisingly small quality loss. Like, how does an LLM survive that level of data destruction?
I mean, the visual analogy is really compelling, but neural networks do not store information like discrete pixels in a texture map.
Okay, so it's a different architecture entirely.
Entirely. Their intelligence is distributed across high-dimensional vectors. They are these incredibly resilient, heavily over-parameterized systems.
Over-parameterized, meaning there's a lot of redundancy built in.
Exactly. We are finding that neural networks just don't actually need 32 bits of mathematical exactness to understand, say, the relationships between words.
Wow.
Furthermore, we aren't just blindly chopping off 28 bits and hoping for the best.
I would hope not. That sounds like a recipe for disaster.
Right. The mechanism of quantization involves dynamic scaling. The system actually looks at a specific tensor, finds the minimum and maximum floating point values, and then calculates the scaling factor.
Oh, so it's tailoring the compression to the specific data.
Yes. It projects that specific range into 16 discrete buckets for an InHay4 representation.
Ah, I see. So we are dynamically scaling the values, effectively normalizing the vector before we compress it.
You've got it.
Rather than just using a hard, absolute cutoff for everything. And I assume we have to establish a 0 point as well.
Yes, that's crucial.
Because you need to ensure that the mathematical 0 in the floating point space maps perfectly to an integer 0. Otherwise, padding operations would just get completely corrupted, right?
That is exactly the distinction between symmetric and asymmetric quantization.
Okay, break that down for me.
Sure. If your tensor's weights are perfectly centered around 0, you can use symmetric quantization and just scale it.
Easy enough.
But if the weights are skewed, you have to use asymmetric quantization and shift the 0 point to capture the distribution accurately.
Oh, that makes a lot of sense.
Yeah. Because of this careful mapping, the network still points in the right general direction. And with billions of parameters pointing together, the overall output remains highly accurate, despite the individual weights being locked into these, well, coarse buckets.
So we're intentionally making the math fuzzier, but we're doing it via a highly optimized mapping strategy.
Precisely.
Which kind of leads us to the question of optimization targets. Like, if Infor is the extreme, where is the operational sweet spot? Because the nodes point directly to In8.
Ah, yes. 8-bit integers. What's fascinating here is that the source refers to In8 as the free lunch of compression.
A free lunch. Oh,
Yeah. For the vast majority of transformer models, In8 quantization preserves over 99% of the model's original quality.
that is wild. 99%.
Over 99%. But look at the sheer performance gains. It halves the memory requirement compared to FP16.
Wow.
And it quarters the memory compared to the original FP32.
I mean, a free lunch. As engineers, we are practically hardwired to reject that premise entirely.
Oh, absolutely. It sounds too good to be true.
Right. The CIP theorem, time-space complexity trade-offs, there is always a catch. You are telling me I can cut my VRAM requirements by 75% compared to the baseline, keep 99% of the intelligence, and there is no hidden performance penalty.
Well, the only penalty is a very minor computational overhead.
Okay, so there is a catch. A tweeny one. You have to multiply the scaling factors back in. But the hardware reality makes that practically irrelevant.
Wait, why is it irrelevant?
Because the architecture of LLM inference is heavily memory bandwidth bound. It's not compute bound.
Oh, right. You mentioned that earlier, the garden hose problem.
Exactly. The processing cores actually spend most of their time just idling, waiting for the massive FP32 matrices to arrive from the RAM.
So the processor's just sitting there twiddling its thumbs.
Yeah. So by switching to Int8, you are moving 4 times the volume of weights across a bus in the exact same amount of time.
That is a massive throughput increase.
It is. Furthermore, modern hardware accelerators like Apple's Neural Engine or NVIDIA's Tensor Cores, they are specifically optimized to chew through Int8 matrix multiplications infinitely faster than floating point math.
Oh, wow. So the model not only fits in your machine's RAM, it actually generates tokens significantly faster.
Exactly. You get speed and size reductions.
We are literally solving the memory bottleneck and getting a hardware acceleration boost at the same time. It's a rare win-win.
It is. But let me push back on this computationally for a second, because this introduces a major architectural paradox to me.
Okay, let's hear it.
If we are deliberately degrading the mathematical precision of the parameters, putting them into these coarse Int8 or Int4 buckets,
Right.
a logical engineer would ask why we are bothering to quantize it all. Wait, from an algorithmic perspective, wouldn't a smaller, mathematically precise model have fewer compounding errors during a forward pass?
That is a really common question.
Because it feels like rounding off 70 billion numbers would result in a massive hallucination multiplier as those errors propagate through, 80 layers of a transformer network.
Yeah, you'd think the noise would just take over.
Great. Why not just train a tight, highly optimized, mathematically perfect 13 billion parameter model from scratch?
It is a totally valid hypothesis.
Mm.
And the compounding error you mentioned is a real concern in deep neural networks.
Okay, so I'm not crazy.
You're not crazy,
Yeah.
but the real-world empirical results show the exact opposite. Yeah. And this leads to one of the most counterintuitive showdowns in modern AI. The source explicitly states that larger quantized models consistently beat smaller precise models.
Wait, so a massive 70 billion parameter model that has been brutally mathematically compressed to 4 bits is actually smarter than a perfectly precise 13 billion parameter model running at FP16.
The benchmarks prove it out consistently.
That is just hard to wrap my head around.
I know, but here is the core reason. Because of the quantization, those two specific setups take up roughly the same memory footprint on your hardware.
Okay, so if I have 40 gigabytes of VRAM, I have to choose how to spend it.
Exactly. And the reason the massive fuzzy model wins is because of the volume of the latent space it learned during training.
The latent space.
Yeah.
Meaning the actual concepts it understands.
Yes. The sheer architecture of a 70 billion parameter model has a vastly wider breadth of combined experience.
It's just seen more of the world.
Way more. It has learned infinitely more complex representations, logic patterns, and coding syntaxes than a 13 billion parameter model simply has the physical capacity to store.
So put it in software terms, it's like having a massive, robust heuristic algorithm versus a tiny, brittle, deterministic one.
That is a brilliant way to frame it.
Like, the 70 billion parameter heuristic might have some fuzzy rounding errors at the micro level, but it has so much surface area covering the problem space that it reliably converges on the right answer.
Exactly.
And the smaller model might execute its math perfectly, but it simply doesn't have the internal logic branches to handle edge cases.
Spot on. The redundancy across 70 billion parameters creates a much more robust mapping. The fuzziness in the individual weights is compensated for by the sheer number of attention heads pointing in the correct conceptual direction.
Scale simply beats precision.
Scale beats precision.
Okay, so clearly, as a developer, the winning strategy is to grab the biggest open source model you can find and quantize it down until it barely fits into your available hardware.
That's the current meta, yes.
Yeah. Which brings us to the actual deployment pipelines. How do we execute this mathematically? Because the notes break down two main methodologies in the developer's toolkit.
Right. Post-training quantization, or PTQ,
Yeah.
and quantization-aware training, or QAT.
Here's where it gets really interesting, because we have to talk about how we handle outliers.
The handling of outliers is the defining difference between those two methods.
Let's start with PTQ.
So PTQ, as the name suggests, is done after the training run is completely finished.
Right, the model is already fully baked.
Exactly. It's fast, cheap, and really accessible. Take a fully trained FP16 model, run a script over it to calculate those scaling factors we talked about, snap the parameters into 8-bit or 4-bit integer buckets, and you're ready to deploy.
Right, but earlier you mentioned that scaling factors rely on finding the minimum and maximum values in a tensor.
I did.
Anyone who has looked at the underlying architecture of an LLM knows that they suffer from massive activation outliers, like certain parameters just spike to extreme values.
Yeah, you get these huge numerical spikes.
So if you blindly apply a PTQ script, one massive outlier weight will stretch the scaling factor to its absolute limit, effectively crushing all the normal crucial weights into a single integer bucket.
It squashes all the useful data.
It's like taking a beautifully rendered 3D physics engine and forcing it to run on an integer grid. The collision detection still sort of works, but objects jitter because they're being snapped to a grid they weren't calibrated for. They're clipping.
That clipping behavior is the exact trade-off of PTQ.
It just degrades.
Yeah. The model never anticipated its continuous mathematical space being abruptly converted into a discrete integer grid, so it suffers a sudden degradation in performance.
So how do we fix that jitter?
To prevent it, and to maintain the highest possible quality at extreme compression rates like E24, you have to use QAT, quantization-aware training.
But hold on, the mechanics of that sound computationally impossible.
Oh!
Yeah, gradient descent, the entire foundation of how a neural network learns, requires smooth, continuous differentiable functions to calculate errors.
That's Calculus 101, yeah.
Right. A quantization function is essentially a step function. It rounds numbers off, and a step function has a gradient of 0 everywhere except at the jump, where the gradient is infinite. If you try to run backpropagation through a rounding function, the gradients would immediately die. The math just shouldn't work.
You have identified the exact mathematical roadblock, and the solution to it is honestly one of the cleverest engineering hacks in modern AI.
Okay, I need to hear this.
It is called the straight-through estimator, or STE.
Straight-through estimator.
During quantization-aware training, you do the forward pass of the data using the simulated, discrete, low-precision numbers.
Okay, so it guesses using the fuzzy math.
Right. The model makes its prediction, and you calculate the error. But when you run the backward pass to update the network, the straight-through estimator simply lies to the system.
It lies.
It pretends the rounding step never happened. It passes the gradient straight through the step function, as if it were an identity function, and applies those updates to a hidden set of high-precision FP32 weights.
Oh, wow. That is incredibly elegant. So the model learns to route around the quantization damage.
Exactly.
By keeping a high-precision master copy of the weights during training, but constantly forcing the model to evaluate itself based on the snapped, quantized versions, the weights naturally shift themselves into the centers of the integer buckets.
They optimize themselves for the grid.
They optimize themselves for the grid. That is amazing.
The network literally trains itself to anticipate the fuzziness from the very first epoch.
Wow.
And once the QAT process is fully complete, you just throw away the hidden FP32 master weights and deploy the highly optimized Infor model.
So it's a vastly superior neural network.
It produces a vastly superior neural network, but the engineering trade-off is that you have to intervene during the actual training phase.
Which requires massive amounts of GPU compute compared to just, running a PGQ script on a finished model.
Exactly. So for the developer listening, if you are grabbing an open source model off a repository and you just want to run it on your laptop tonight to parse some logs, you are probably using a PTQ tool like llama.cpp.
Right, because it's fast, and block-wise quantization helps mitigate the outlier problem enough for casual use.
Yeah. But if you are a massive AI lab trying to release the absolute best-in-class tiny model specifically engineered for mobile phones, you are investing the millions of dollars in compute to run QAT from scratch.
The compute budget entirely dictates the deployment pipeline,
QAT is an investment in ultimate edge device performance.
which naturally leads us to step back from the specific algorithms for a second and look at the broader tech ecosystem.
Let's do it.
Because this isn't just a neat trick for saving hard drive space on an AWS instance. The notes state categorically that quantization is the literal engine that enabled the open-source LLM revolution.
It really is.
Without it, running powerful language models on consumer hardware would be completely impossible. So what does this all mean?
If we connect this to the bigger picture, it means the total decentralization of artificial intelligence.
Decentralization.
Yeah. We have talked in previous deep dives about the major transformer architectures,
Yeah.
the attention mechanisms, and the massive scaling laws.
Yeah.
But all of those incredible breakthroughs would be permanently locked behind the API walls of 3 or 4 massive tech companies if it weren't for quantization.
Right, because without the ability to map FP32 to NT4, you would literally need a multi-GPU server rack in your living room just to run a local coding assistant.
It would be incredibly restrictive.
The barrier to entry would exclude almost every independent developer on Earth.
Quantization takes a piece of technology that costs tens of millions of dollars to train and squishes it down so that you can run it entirely locally on an M-series MacBook or a standard gaming PC.
It breaks the API monopoly.
It really does. It allows researchers globally to experiment with these architectures without needing a government-funded supercomputer.
And more importantly for the software engineers listening, it allows you to build private, offline AI tools.
Oh, the privacy aspect is huge.
Yeah, you can pass your company's proprietary source code into a local LLM to check for vulnerabilities, knowing with absolute mathematical certainty that the data never leaves your machine.
It secures the data, and it levels the playing field for innovation.
It really does, and it sets up our next step perfectly.
Yeah.
Because now that we know exactly how to compress this massive generalized intelligence so it fits on our laptops, the next phase of our source material, which we will tackle in our next deep dive, shifts to how we actually fine-tune them.
Ah, yes.
We will look at techniques like LoRa and explore how you take that compressed general-purpose Infor brain and adapt it into highly specialized tools.
Like a dedicated code reviewer or an automated QA tester.
Exactly.
It is the necessary progression of the stack. First, you build the architecture, then you quantize it to fit the deployment hardware, and finally, you fine-tune the weights to perfectly match the specific engineering task.
So, to quickly recap our technical journey tonight, we started by looking at the great mathematical squeeze, replacing 32-bit floating point numbers with dynamically scaled 4-bit integers to overcome the crippling memory bandwidth bottlenecks of consumer hardware.
Essential for edge deployment.
We discovered that N8 is the elusive free lunch of computer science, keeping 99% of the quality while allowing hardware accelerators to chew through matrices at blistering speeds.
The hardware loves an A.
It really does. Then we resolved the scale versus precision paradox, learning exactly why the massive latent space of a fuzzy 70 billion parameter model will always beat the brittle perfection of a 13 billion parameter model.
Scale beats precision.
Every time. And finally, we broke down the engineering pipelines, contrasting the quick, clipping-prone nature of post-training quantization against the rigorous, gradient-faking brilliance of quantization-aware training and the straight-through estimator.
All of this underlying mathematics is exactly why you, the developer listening right now, can actually instantiate these models in your local environment.
It's empowering, really.
Quantization is the fundamental bridge between theoretical AI research and practical, everyday software engineering.
So keep pushing what that local hardware can do. Keep experimenting with the open source weights and keep building your own pipelines. But before we let you get back to your IDE and that build process, we want to leave you with one final lingering thought to mull over based on the physics we covered tonight.
Yeah, we established today that the sheer volume of a 70 billion parameter model allows it to easily survive the mathematical fuzziness of being compressed to just 4 bits,
Right.
which raises a fascinating trajectory for the future of inference. Where is the ultimate mathematical floor?
How low can we go?
Exactly. If an architecture is robust enough to handle 16 discrete integer buckets, what happens if we compress the parameters down to just 1 or 2 bits?
1 bit.
Yeah. We are already seeing the theoretical beginnings of ternary models, where weights are simply represented as -1, 0, or +1.
That is insane.
Could the future of edge computing be trillion parameter models running flawlessly on everyday mobile phones, powered by a neural matrix that is essentially reduced to simple coin flips?
It is wild to think about a massive, globally aware intelligence running on almost no mathematical precision at all.
It's coming.
Keep that concept in mind next time you hit compile. Thanks for joining us on this deep dive. Keep diving deep, and we'll catch you next time.